Please welcome Andreas Kolb, Universität Siegen.
Modern computers seem powerful, but they break at hard limits. And limits on falling walls are no obstacles, but meant to be overcome, right? So today is about one of the hardest, the limit of small-scale quantum computing. I'm Andreas Kolb, Vice Rector of Research at the University of Siegen, and yes, a computer scientist. But when Michael Johanning and Christoph Wunderlich from our experimental quantum chair came up 15 years ago with their ideas, I was thinking, fantastic idea, never practical. Now, here we are. eleQtron is founded in 2020, already building quantum machines for DLR and Forschungszentrum Jülich, with 80 brilliant people at sites in Siegen and Hamburg. Their trapped ion quantum computing technology makes them unique. They don't need fragile laser beams, but they use magnetic and use quantum control to get stable qubits at the end of the day. So eleQtron is paving the path towards scalable quantum computing in Germany, and Michael Johanning will explain you how this is done.
Breaking the wall of small-scale quantum computing. Michael Johanning, eleQtron.
Computing is everywhere, and it's a success story. So the question is, where is the problem? And to see the limits and where maybe quantum is actually a good thing to go further, we should look at the things where classical computers don't perform so well. And among the problems where they don't perform so well and quantum could have huge impact are really big ones. For example, in chemistry simulations for material research, we just heard about that. And there is potential in quantum to improve battery efficiency, to widen the applicability of superconductors, to revolutionize drug discovery and therefore our healthcare system. There are optimization problems that can be addressed by quantum that would allow us to reduce our footprint, CO2 footprint. So the question where quantum has an impact is also a lot of the question how to save the planet. So when I advertise quantum, I need to address why there is this huge potential. And there are at least two good answers. In chemistry simulations, we really simulate something that is based on quantum. So basically, quantum computers work on their home turf. In optimization problems, we are going through a number of possible solutions, and we are using the fact that quantum computers use qubits, which can be in two states at once. And that means 2 qubits can be in 4 states at once, 3 qubits in 8, and so on and so on. And therefore, you can utilize that to sample the solution space exponentially faster. So you do not go through solutions in sequence as a classical computer, but do that in parallel. So there is the potential, yes. And we actually have seen proof of concept, and that's all there. So where are we stuck? Well, we can use only small systems to do toy problem proof of concepts, and that is based on 3 facts. The qubits that we are using are kind of fragile. They do not keep their memory forever. We need to make them better. We need to make the operations on them better. We need to connect them so they can exchange information, and that's a key to make very efficient algorithms and to change the point at which they overcome the performance of classical computers. In the end, we need to make much more qubits because we need to make the problem size so big that it becomes interesting. And what eleQtron does is it combines several things that actually address all of this. We use atomic qubits, which have world record memory time. We use them in trapped ions, so these ions all interact directly with each other, giving you all-to-all connectivity, the best you could have to make the most efficient algorithms. And we use microwave control to make the algorithms, which is actually already scaled and proven. You have all of that in your smartphone. And so the key recipe for eleQtron is we combine ion traps and microwaves. And these 2 ingredients pay on the problems that we just said, on quality of qubits and the connectivity and on scalability. So where are we? eleQtron founded in 2020, now grown to over 80 people, distributed over 2 locations. We are building machines for DLR and Jülich Research Center, and we have more than 30 patents that are already granted and more to come. And the near future, this was actually not a rendering, but a real machine. The near future will actually be to integrate much of the control periphery into the chip. So that is signal generation, photonics, and this is actually one of the chips created with our partner Infineon that is one step in this direction. So here we are coming and building upon research that is over 20 years of academic work and combining that actually with the talent, with the flexibility, agile methods, other resources that only a startup can provide. And therefore, we believe magic actually can be the Zukunft of quantum and can be one way to break the wall of small-scale quantum computing. Thank you.
The magic of quantum. I love this. Ready for questions? Inga, you're going to start? Thank you.
Perfect. Thank you very much. Very impressive. So who are your customers right now? Because you talked about partners and how you plan to industrialize, because I think that might be very critical for the scaling part.
So the customer landscape at the moment is fairly artificial because the machines are not there yet. So our customers are research customers like DLR and Research Center Jülich, where it is about also to develop quantum algorithms and fully use the power of them. In the future, the model is completely different. We are also not into selling machines really, but we want to sell computation time. So we'll partner up with hyperscalers, high performance computers, and actually develop quantum as a module to be offered to the customer. So you don't need to think in the end about quantum. You should just click the check mark, I also use quantum, and get a boost on certain problems, not all problems.
Thank you. Mali, you're the next one. Thank you.
Thank you very much. You know, in the EIC fund, we are the biggest, I would say, investor in quantum. We have the biggest portfolio. My question is, and you explained that a bit, what is the leverage you bring in? And I mean, I'm asking this because what is the biggest challenges right now for you to really scale? Because usually the problem is you're great in innovation, but the problem is that you're stuck too much long in lower TIL and there's no scalability.
Yes, absolutely. So one can talk about every platform and the world records that you make, but it's actually not just about world records. The question really is about roadblocks. And we have many platforms and they all deserve actually attention and have potential, but to avoid roadblocks is the key thing. And so we avoid roadblocks like very fragile and sensitive lasers, and therefore simplify the integration into chip, which is actually the thing to scale up.
Mm-hmm. We'll go further with Iris first, and then back to Inga and Stefan first. Iris first, sorry.
You mentioned in some applications customers could benefit from quantum and getting a boost there.
Yes.
Which specific applications from an industrial perspective do you target?
Yeah, so the one is huge because it's everywhere is optimization problems. Many optimization problems are actually really that you need to check all options, like having a set of keys and trying to get the best one. And there quantum has the advantage that it can try them all out in parallel and give you the best one. You can also have heuristics, but they don't give you the best one, but a pretty good one. And sometimes it's worth the difference.
Mm-hmm. Inga, you had already a question. I'll leave the priority to Stefan, please. Then back to you.
You have an impressive number of patents already. Which are the ones that make it a key differentiator to your competitors, which are very well invested with billions of dollars?
So I mean, we come from research. So the first thing that you do is you publish, right? And you make it open to everyone. But when we recognize that this is worth making a company, what we patented was the step to go from the proof of concept into making it scalable. So all the things, the technology, how it's utilized on a chip level, that is what we patented. And so this is difficult to get around.
Okay, Inga, you have probably the last question.
I would love to understand your management team, your executive team, because I think you are the CTO and you have a professor.
Correct.
So
Yes.
who is taking care of fundraising, of sales, of stuff like this?
Correct. So the professor is basically the academic branch, and not so much important on the everyday business of the company. We do have a CEO. He has actually really a deep background in running companies up to 500 people and so on. And partners and people in our company who know the scaling process up to a few hundred people. So there is a strong DNA about business in our company that is quite unusual in the quantum business, I would say.
I think we're done with 4 seconds. Thank you very much for all of these answers.